I have control?
Yes, you do.
All right, you want to start? Okay, Alex, we'll start. Okay, good afternoon. Thank you for joining us again. Today, Frank and I are going to be talking about the ideas about multiplication and addition through the grade.
Okay, so we're going to look at a situation. There are 3 boxes, and in each box contains 24 apples. So the question is, how many apples are there? Okay, so we know that what we're going to do with this is we're going to multiply. Okay, this means that we're going to multiply 24 times 3. Okay. Now what we're going to do is we're going to look at a set of videos that looks at 24 times 3 in a standard procedure way. And what we'd like to do is start with that as a base and then move through the use of multiplication and addition as we move through our idea about algebra being a generalization of arithmetic. So let's start with looking at our video. Let's look at the number 24, and we should represent 24 using 2 tens and 4 ones. But suppose we want to show 3 sets of 24. Well, here's one set of 24. Here's another set of 24. And here's a third set of 24. So now we have 24 3 times. So we have 24 once, twice, 3 times. And we want to find the total that we have when we have 3 sets of 24. Well, the first thing we can do is we can put the ones together. So we have putting all these ones together this way, count them here. We have 2, 4, 6, 8, 10, 12 ones. But since we only want to use these pieces and we only want to keep less than 10 ones in the ones place, we can trade 10 of our ones for a new 10. So we can trade 10 of our ones for a new 10. And we place the new 10 up here with the other 10. So that leaves us with 2 ones. Now let's put our 10s together. We're going to start with the 10s from the original problem. We had 6 10s. We put them together. And then we add in the new 10 that we got when we traded. And so now we have 1, 2, 3, 4, 5, 6, 7, 10. And we have 2 ones. So when we have 24 3 times, we have an answer of 72. And the reason we have this is we traded 10 of our ones for a new 10. We're going to talk about multiplication of whole numbers. And I'm going to start with the number 24. And I'm going to represent 24 as 2 10s and 4 ones. And I'm going to record that. 2 10s and 4 ones. Now the question we want to answer is, what is our total if we have 3 sets of 2 tens and 4 ones, or 3 sets of 24. So let's show 3 sets of 24. Here's one set of 24. Here's another set of 24, or 2 tens and 4 ones. And here's a third set of 2 tens and 4 ones. So now we want to find this total. We now have 24, or 2 tens and 4 ones, 3 times. So we're going to record that. We have 2 tens and 4 ones, 3 times. Now let's find the total. We'll start with the 1. We have 3 sets of 4 ones, and that's going to give us 2, 4, 6, 8, 10, 12 ones. But we know we don't want to have more than 9 ones in the ones place. So what we can do is we can trade 10 of these ones. Let's take 10 of the ones. 2, 4, 6, 8, 10. We can take 10 of our ones and trade them in for a new 10. And we can place the new 10 up above the 10, and we take away our ones that we traded in. So that leaves us with 2 ones and a new 10. And let's record that. When we took a set of 4 ones 3 times, that gave us 12 ones. We traded 10 of our ones for a new 10, so that gives us a new 10 up here. We record that there. And that leaves us with 2 ones, as we have right here. Now, let's do the total for the 10. Let's do the 10s from the original problem first. We have 2, 4, 6, 10. And then we add in our new 10. So that gives us 7 tens. And let's record that. So we had 2 tens, 3 times. That gave us 6 tens. And then the new 10 and it gives us 7 tens. So now we have 7 tens and 2 ones. So when we have 2 tens and 4 ones and want to find the total, if we have that amount 3 times, our answer is 7 tens and 2 ones. And the reason we can do that is that we traded 10 of our ones for a new 10. We're going to start with the whole number 24, and we're going to represent that with 2 tens and 4 ones. And let's record that. So we have 2 tens and 4 ones. Now what we want to do is we want to find out how much we have if we have 2 tens and 4 ones 3 times. In other words, 3 sets of 24. So here's the second set of 24. And here's the third set of 24. So now we have 1, 2, 3 sets of 24. Now, the 3 is not a quantity someplace else. It just represents the number of times that we have 24. So we're going to write it in red. And we're going to say that we're going to have 24 3 times. Now, let's look at our total. Let's look at our ones. We have 3 sets of 4. And we put those together. And we have 2, 4, 6, 8, 10, 12 ones. So So now what we can do is, since we only want to keep less than 10 ones in the ones place, we can trade in 10 of these ones for a new 10. So let's do that. So we take 10 of our 1, 6, 8, 10 of our 1 for a new 10. Now let's stop right here and record what we've done. We've taken our 12 ones because we have 4 sets of 10 times 3, and we've traded them in, and now we have 2 ones left. We traded 10 of our 1 for a new 10, and let's record our new 10 in the 10 column. Now let's look at our 3 sets of 2 10s. 3 sets of 2 10s will give us 6 10s, and the new 10 will give us 7 10s. So now we have 7 10s, and let's record that. So when we have 24 3 times, our answer is 72. 10, 20, 30, 40, 50, 60, 72. And the reason we have that is because we traded 10 of our 1 for a new 10. Okay, so that's the standard multiplication algorithm that we've all seen and know about. But what we want to do is talk about other ways of doing it and how that can be generalized into the algebra. So here's another way of looking at that multiplication. We have 24 times 3. The first thing we can do is we can multiply the 3 times 20, and that's going to give us 60. The next thing we're going to do is we're going to multiply 3 times 4, and that's going to give us 12. And when we add those two subtotals, we get 72. And this is called the display method. It displays each of the subtotals. There is no regrouping. There is no trading. It basically says exactly what the quantities are after each multiplication.
Now, we can do this with double digits. We have 35 times 13, so we can take the 3 times the 5, get 15. 3 times the 30, get 90. 10 times 5 will give us 50. 10 times 30 will give us 300, and if we add them up, we get 455. You can do it with double digits, single digits, and a double digit, so it's the same thing. It's the display method of displaying, as some call it, the partial sum. And this is what we're looking at, of being able to take regrouping.
And finally, we can compute it horizontally. The way we'll do mental math. And as we do this, I want you to think about what is 3 times 24, or how would you do it mentally? Now, the process is that we have 3 times 24, and we can write 24 as 20 plus 4. And if you go back to the problem that we did vertically, you will see that we're just setting up the 20 and the 4 again. And so we have 3 20s, 3 times 20, and 3 4s, which gives us 3 times 4. Finally, 3 times 24, if we look at what we've done, we broke up 24 into 20 plus 4. That's the second line. On the third line, we have 3 times 20 plus 3 times 4. The 3 times 20 gives us 60. The 3 times 4 gives us 12. And the total becomes 72.
Well, we can take the problem we did before, and we can write it in the expanded notation. And we can state that 35 is 30 plus 5. The 13 is 10 plus 3. And doing the same thing. We get the 3 times the 5, the 3 times horizontally, just as we did before, and again, it's with double digits. So you have 30 plus 6 times 40 plus 4. I'm going to take the 30 times the 40, the 30 times the 4, the 6 times the 40, and the 6 times the 4, and you will get it in vertical or horizontal notation. You'll get the answer of 1,584. So if you look at this, this is the display method, and the other method could be leading us into what we call the distributive property method. We can also do it by a picture. Here's a picture, and we can see that we have 10 plus 9 times 10 plus 6. So if you look at this, you can see that again, if we use the 10 by 10, the 9 times 6, and the 9 times 10, and the 10 times 6, you will get the answer. And here would be the picture of it.
And all of these are examples of the distributive property of multiplication over addition for whole numbers. And let's just make a point here. Sometimes, and I think we've mentioned this before, sometimes when we know this stuff and we're trying to teach it and trying to move through it, we get what we have dubbed as math slang. And so the slang is kind of language structure where you kind of know what's going on already as people talk to you about it. And sometimes we in mathematics get into what we call math slang, where we would just say the distributive property. We think it's very, very important that as you do this, you talk about always the distributive property of multiplication over addition. It's important for the children to understand that that's the complete property and not just distributive property. So what we're going to do now is we're going to look at another example. And again, we have 3 times 2 and a 4. This means, and here are some videos to show again the kinesthetic, the language connecting, and the introduction to symbols models for doing these types of problems. 2 and a 4. We're going to look at a mixed number, 2 and 1/4. Now what we're going to do in this video is look at what happens when we have 2 and 1/4 a few times. Let's say we're going to have 2 and 1/4 3 times. So let's put that down. So there's our first set of 2 and 1/4. Here's another set of 2 and 1/4. And here's a third set of 2 and 1/4. So now we have 3 sets of 2 and 1/4. Here's one set of 2 and 1/4. Here's another set of 2 and 1/4. Here's a third set of 2 and 1/4. So we have 2 and 1/4, 1, 2, 3 times. What is our total? Well, let's put the fractions together first. We have 3/4. Now let's put the ones together. We have 1, 2, 3, 4, 5, 6, 1. So if we have 2 and 1/4 3 times, our answer is 6 and 3/4. Because what we're doing is we're putting the fractions together and we're putting the whole numbers together for the 3 sets. Let's look at the mixed number 2 and 1/4. And let's record. So we have 2 and 1/4. What we want to do is we want to see what we get when we have a few sets of 2 and 1/4. So let's talk about 3 sets of 2 and 1/4. So there's one set of 2 and 1/4, and we recorded it there. Here's And here's another set of 2 and 1/4. And let's record that. Now the question is, what is our total? In other words, what do we get when we put together 3 sets of 2 and 1/4? We have 1 set here, recorded, 1 set here, recorded, 1 set here, and we record it here. The first thing we do is we put the fourths together. We have 3/4. We put them together, and we get 3/4. So our total is going to be 3/4 because we have 1/4 3 times. Now let's put our ones together. We get 2 1s, 2 1s, and 2 1s. So we have 1, 2, 3, 4, 5, 6. We have 3 sets of 2, and 3 sets of 2 is going to be 6. So when we put together 3 sets of 2 and a 4, our answer is 6 and 3/4. And the way we do that is we take 1/4 3 times, and then we take 2 1s 3 times, and that gives us an answer of 6 and 3/4. Again, we're going to look at the mixed number 2 and 1/4. And we're going to record that using fraction symbol. So we record that as 2 and 1/4. And the question is, what happens when we have 3 sets of 2 and 1/4? What do we get as a total? Well, that means we want to take 2 and 1/4 and multiply it by 3. Because we want to have 3 sets of 2 and 1/4. So let's show our 3 sets of 2 and 1/4. Because that's what we mean when we say we want to multiply it by 3. It means we want 3 sets of 2 and 1/4. So there's 1 set of 2 and 1/4. There's another set of 2 and 1/4. And there's another set of 2 and 1/4. Now let's find the total. Well, the first thing we know is we have 1/4 3 times. We have 1/4 3 times. And 3 times 1/4 is going to give us 1, 2, 3/4. And we record that here. Now we have 3 sets of 2. So we know that 3 sets of 2, or 3 times 2, is going to give us 6. So we have 3 sets of 1/4, which gives us 3/4. And then we have 3 sets of 2, which gives us, we have 3 sets of 2 and 1/4. Our answer is going to be 6 and 3/4. We're going to look at the mixed number 2 and 1/4. And we want to find out what we get as a total when we have 3 of these. In other words, 3 sets of 2 and 1/4. Or another way of saying it in mathematics is when we multiply 2 and 1/4 times 3. What we do is we find out what 3 of each of these is going to be. So let's look at our fraction 1/4. 3 times 1/4 means I have 1/4 3 times. If I have 1/4 3 times, that gives me 3/4. 3 times 2 means if I have 2 3 times, I have 2, 2, and 2. 2 plus 2 plus 2, or 3 times 2, and that's going to give me. So if I multiply 2 and 1/4 times 3, the first thing I do is I multiply 3 times the 1/4. It means I have 1/4 3 times. It means I have 3/4. Then I multiply 3 times 2, And we know that 3 times 2 is 6. So 2 and 1/4 times 3 is a total of 6 and 3/4. So now let's look at another problem. Here we have 4 times 3.5, or 4 times 3 plus a half. It's going to be 4 sets of 3.5. And notice the way the language in working with, whether it's horizontal or vertical, the language remains the same. I have 3.5 4 times. If I have 3 4 times, I get 12. If I have a half 4 times, I get 2. And so therefore, we have 14 as our total. So we have 4 times 3.5 will give us 4 times 3, or 4 threes is 12. 4 halves gives us 2. And then the total gives us 14.
All right, we can do this with a picture model. Here is 3 1/2 times 1 2/3. So if you look at the horizontal axis, it's been broken up into 3 plus a half, or 3.5. And if I look at the vertical axis, that's been broken up into 1.5. So if I take, and looking at a half times 3, I'm sorry, 1 times 3, can't read, 1 times 3, for the first rectangle, I get 3. A half times 3, and so I'm getting my answers. And if I take this, I get 3 times 1, which will give me 3. 3 times 2/3, which will give me 2. And then I get a half times 1, which will give me 1. And a half times 2/3, which will give me 2 6. And if I add them up, I get 5 plus 3 6 plus 2 6, which will give me 5 and 5 6. So you can do it with picture model also.
And if you'll notice, what it really comes down to is almost taking the numbers that represent, the numerals that represent one number, and taking the numerals that represent the other number, and multiplying everything by everything. If you really want to look, if you look at this example, in the first number we had 3.5, or 3 plus a half. And the second number we had 1 2/3, or 1 plus 2/3. And what happens is you have everything being multiplied together, and that gives you your answer. All of these are examples of the distributive property of multiplication over addition for multiplying a mixed number by a whole number. So now let's think about this in a general way and how we can write all of this. So let's think about a problem where we have a rectangle where one side is 2 and the other side is 4a plus 3. Now we know the area of our rectangle is equal to the length times the width. So here we have a diagram. Our width is 2 and our length is 4a plus 3. And we know the formula for the area is length times width, so we write area equals 2 times the brackets, or the whole thing, of 4 plus 3, 4a plus 3, I'm sorry. Now if you'll notice how this is parallel in many ways to what we've done before. A whole number times 2 things being added together. And that's the essence, in a sense, of the distributive property for a single digit by a multi-digit. So we have area equals length times width, and we write this as, where does 7 come from? I'm sorry, that's, wow. So we have 7 times 2n plus 3, and this means that we have 7 sets of 2n and 7 sets of 3. Okay? Now, what we're going to do is we're going to look at a distributive property of video, which shows what we've been talking about. We're going to start with the expression 2a and 3. So we're going to have 2a's and we're going to have 3 ones. And the question we're going to be talking about is, what happens if we have more sets of 2a and 3? Well, let's add the second set of 2a and 3. So here's a second set of 2a and 3. Now we can deal with this in two ways. The first way is that we have two sets of 2a and 3. Here's one set of 2a and 3. Here's another set of 2a and 3. Or what we can do is we can put all the like things together. So what we can do is we can say we put all the a's together and we put all the ones together. And now we have 4a and 6. So what we can do is, in dealing with the expression 2a plus 3, and if we have two of them, we can either say that we have two sets of 2a and 3, one here and one here, or that we have one set of 4a and 6, 4a and 6. We're going to start with the expression 2a and 3. So we're going to have 2a's and we're going to have 3 ones. And the question we're going to be talking about is, what happens if we have more sets of 2a and 3? Well, let's add the second set of 2a and 3. So here's a second set of 2a and 3. Now we can deal with this in two ways. The first way is that we have two sets of 2a and 3. Here's one set of 2a and 3. Here's another set of 2a and 3. Or what we can do is we can put all the like things together. So what we can do is we can say we put all the a's together and we put all the ones together. And now we have 4a and 6. So what we can do is, in dealing with the expression 2a plus 3, and if we have two of them, we can either say that we have two sets of 2a and 3, one here and one here, or that we have one set of 4a and 6, 4a and 6. Let's look at the expression 2a and 3 ones. So we show 2a's and 3 ones, and let's record them. So we have 2a plus 3. Now, the question we're going to look at is, what happens if we have more sets of 2a and 3? Well, let's look at another set of 2a and 3. Here's 2a's, and here are 3 ones. So now what we have is, we have two sets of 2a and 3 ones. We have doubled it. So in mathematics, what we say is we have taken 2a plus 3 and we've multiplied it by 2. Now we can deal with two sets of 2a and 3 ones just as it is here, or we can put like things together. So let's do that. We put the a's together and we put the ones together. And let's record what we have. Well, we have two sets of 2a, and that gives us 1, 2, 3, 4a. And we have two sets of 3, which is 1, 2, 3, 4, 5, 6, two sets of 3 will be 6. So when we deal with this expression, 2a plus 3, if we look at it, two of them, we can have two sets of 2a plus 3, or 2 times 2a plus 3, or we can say we put everything like together and we get 1, 2, 3, 4 A's and 1, 2, 3, 4, 5, 6. Now, one thing we want to remind you is that in saying this, we actually say 2 times the quantity 2a plus 3 to show that we have two sets of 2a and 3. And so 2 times the quantity 2a plus 3 gives us 4a plus 6. We're going to start with the expression 2a plus 3. And the question is, what happens? We have more sets of 2a plus 3. Suppose we have 2 of them, which means that we want to double 2a plus 3. That means we're going to say 2 times the whole quantity should be 2 times 2a and 2 times 3. We can then say that we actually have, in this quantity, we actually have 2 sets of 2a, and that's going to give us 4a. And then we're going to have 2 sets of 3, and that's going to give us 6. Another way of saying this is 2 times 2a is 4a, and 2 times 3 equals 6. So 2 times the quantity, 2a plus 3, gives us 4a plus 6. And this is called distributive property of multiplication over addition. You have 2 times the quantity, 2a plus 3, is going to give you 2 times 2a is 4a, 2 times 3 is 6. So the multiplication 2 times 2a plus 3 is going to give you 4a plus 6. And this procedure is called the distributive property of multiplication over addition. So this is an example of the distributive property of multiplication over addition for multiplying in algebra. But remember, when in algebra we use the distributive property of multiplication over addition, we are just showing a generalization of how it is used in numbers. For example, if you go back to our original problem, we had a multiplication of a whole number times a whole number. Then we had a multiplication of a whole number times a mixed number. All of those are the distributive property of multiplication over addition. And what algebra basically does is take that idea and then says, this is the way it generally looks, in a sense. So then the last one we had showed that it was a multiplication. Now the point is that you cannot add those things together because you have a's and 1. But the idea is that it is still the distributive property of multiplication over addition.
So where does this lead us? This leads us to the generalization if we have 2 quantities, x plus y times x plus y. And here's a picture model as we showed before. All of this is leading up to the fact that we can do this with a double digit and a single digit, 2 double digits, and the different various ways of representation, expanded notation, either vertically or horizontally, using a picture as a diagram as we've done here using the area model. So if I take my x plus y times my x plus y, you see similar to the expanded notation picture model we had before, I'm going to get x squared, x times y squared. And now that would lead us to the solution of x squared plus 2xy plus y squared, similar to the previous problem, that I could not add my a's and my 1's. I cannot add my x squareds and my y squareds, but I can add my x, y's. So therefore, my final solution then is x squared plus 2xy plus y squared. This is the process of starting in the elementary, moving it up through the grades to the algebra and giving them a basis of where the distributive property and how the distributive property is developed in leading us to that.
So all of these examples show how we can use the distributive property of multiplication over addition. On a curriculum basis, one of the things you have to think about is how is the third and fourth grade teacher, who possibly is doing a 2-digit number times a 1-digit number, how is that person going to communicate with the 5th and 6th grade teacher who is doing it with a mixed number times a whole number, and how is that going to communicate with the middle school people in 7th and 8th grade who are doing it algebraically? And that's a district concern, but that's the idea. That's what has to be done for those people to communicate, so that the one child, in a sense, going through all of this sees a pattern that's building, as opposed to seeing something in 3rd and 4th grade, something in 5th and 6th grade, and then finally something in 7th and 8th grade that's called the distributive property of multiplication over addition.
It builds over the grades so that you're giving them a thorough understanding of what the real concept of multiplication over addition really means. So they're developing a sense of going through it with numbers, expanded notation, pictures, leading it up to the generalization of the abstract. So it's taking it through the grades, looking at this, and developing a solid foundation of the distributive property as stated as multiplication over addition.
So here's another idea of multiplication and addition through the grades. What we're going to do is we're going to start with a simple buying problem. Wanda buys 2 sandwiches for $7 each and 3 bottles of juice for $4 each. How much did she spend in all? Now, to find out how much Wanda spent, we first find the cost of the sandwiches and the cost of the juice, which is a normal thing to do. So we can write it out this way. We have the cost of everything equals the cost of the sandwiches plus the cost of the juice. It means the cost of everything is 2 times $7, that would be the total cost of the sandwiches, plus 3 times $4, which would be the total cost of the juice. So the cost of everything would be $14 plus $12, and that would give us $26. Now let's notice the pattern that occurs, because we're going to talk about generalizing this. The first action was to find the cost of the sandwiches and then the juice. And to do this, we multiply. The second action was to find the cost of everything. And to do this, we added the 2 answers from part A. So first we multiplied, and then we added. And it was not that there was any rule involved. It's basically that's the way you do it. If you're buying sandwiches and juice, and you're buying multiple parts of them, then you multiply by the cost of the sandwiches times the number of sandwiches, and the cost of the juice times the number of juices, and then you add everything together. That's the natural way of looking at it. And we call this in mathematics the order of operations. And I know there's been a lot of talk about where it came from. You know, I think the one area was that it was a group of mathematicians who thought about this. And that really isn't true, because there's no significant note in the history of mathematics that shows that. Well, at least Maria and I didn't get the memo. Okay? But why did we do that? Again, is because it's the natural way to find the answer. So the equation is T equals 2 times 7, which is the cost of the sandwiches, plus 3 times 4. In this way, it says we have 2 7s and 3/4. So we multiply and then we add. With the equation 2 sevens and 2 times 7 plus 3 times 4, would it make any sense whatsoever to add the 7 and the 3? The answer is no. Not so much because of our problem, it's because of what we're talking about also. For example, in our problem, the 7 stands for dollars, and the 3 stands for 3 sandwiches. And you don't add dollars and sandwiches. They don't have the same last name. So you must multiply and then add. Why? Because it's the natural thing to do. No rules, just reality. Let's look back at that equation again. Let's look at t equals 2 times 7 plus 3 times 4. What we have here is we have 2 sevens and 3/4. 2 tells us how many sevens we have. 3 tells us how many 4s we have. So we keep them together. What we have found, however, there is almost a compulsion on the part of anybody looking at that to add the 7 and the 3 first. It just seems to be the way people think. However, it's not the natural thing to do. But what happens when we have the equation 7 times 2 plus 3 times 4 with no context? How do we explain it? And again, let's look at 2 times 7. 2 tells us our quantity, and 7 tells us our quantity, and 2 tells us how many we have. It's like 2 times 7 means 2 sevens. So when we write the equation using this idea, we have 2 times t equals 2 times 7 plus 3 times 4. T equals 2 sevens plus 3/4. And notice what we've done here. We've actually written out the groups that we have, and the numerals are the number of groups. You could look at it in language terms as 2 times 7, meaning you have 2 sevens. 7 is my quantitative noun. It tells me what I have. 2 is my quantitative adjective. It tells me how many I have. And before I can find a total, I have to deal with my quantitative adjective and my quantitative noun. So when I have t equals 2 times 7 plus 3 times 4, I can't add 7 and 3 because in a sense, 7 is a noun linked to 2, and 3 is an adjective linked to 4. And I think we all know that I do not add nouns and adjectives. So this means that learning the order of operations can begin as early as 3rd and 4th grade when students do these types of problems. There is not a problem with doing this. I think the problem sometimes is children do not hear the term order of operations until we're trying to teach it all at once in the upper grade. And again, as I mentioned before, here again we have a school idea. What part of the order of operations are we going to teach in 3rd and 4th grade? And what part of the order of operations are we going to teach in the upper grade? And beware of compulsion for closure, where teachers feel they have to teach it all at once. Let the order of operations grow through the grade. So let's look at this number, 3,729. And we can expand this to 3 times 1,000 plus 7 times 100 plus 2 times 10 plus 9. Now, we can take that 3 times 1,000 plus 7 times 100 plus 2 times 10 plus 9, and we can be a little more sophisticated in our symbolic writing. In, say, 6th or 7th grade, where we can have 3 times 10 to the 3rd plus 7 times 10 squared plus 2 times 10 plus 9. Now, I just want to let you know, we've made the decision not to talk about 10 to the 0. In this case, right now, it just kind of muddies the water a little bit. So we went from 3,729 all the way down to 3 times 10 to the third plus 7 times 10 to the second plus 2 times 10 plus 9. Now, how do we go back? That is, how do we go from 3 times 10 to the third plus 7 times 10 squared plus 2 times 10 plus 9 and get back our original number, 3,729? The first thing we do is we compute the powers of 10. So we have 3 times 10 to the third gives us 3 times 1,000. 7 times 10 squared gives us 7 times 100. 2 times 10 gives us 2 times 10, and then plus 9. Now, if you'll notice, this leaves us now with multiplications and addition. We've taken care of our exponent. If we had, look up at the top, if we had multiplied 3 times 10 and then taken it to the third power, we would be well beyond 3,000 by that time. So we do our powers first. Now, once we have these, now we multiply. Going back to our original problem of buying the juices and the sandwiches, we now multiply. So we have 3 times 1,000 gives us 3,000. 7 times 100 gives us 700. 2 times 10 gives us 20, and plus 9. And now we add. 3,000 plus 700 plus 20 plus 9 gives us 3,729. And here is our entire sequence. We started with the exponent. We then went to the expanded notation. Then we went to more common expanded notation. And then finally, we went down to our original number. And in doing all this, we went certain ways. We went from 3 times 10 to the third plus 7 times 10 to the second plus 2 times 10 plus 9. We went down to 3,729. The first thing we did was we calculated the exponent. We calculated the exponents first. So in calculating, this is kind of step 2. So in calculating with the order of operations, we calculate exponents, then we multiply, and then we add. And if you'll notice, we're not talking about a rule of the order of operations here. We're really talking about the way we would normally do things with numbers. And this is why it's important to start this in the early grade, so that the students realize that these aren't rules that are made up. These are rules that come from numbers and their work with numbers. So the order of operations is calculate, exponent, multiply, and then add. Now, of course, in the order of operations, we have to talk about parentheses. And what do parentheses really do? Sometimes parentheses postpone the order of operations. So what we want to look at is, let's look at this example. 6 times the quantity 4 plus 8. Okay? So the first thing we have to do here is, this means we have 6 sets of 4 plus 8. Now, if you'll remember back when we were doing it with the algebra, we had 2 sets of 2a plus 3. We couldn't add those because you can't add 2a and 3. And although they were in parentheses, they should have been done first. But again, they couldn't be done because you can't add 2a and 3. In this case, we can add 4 and 8. And when we add 4 and 8, we get 12. So the parentheses tell us, it is not that the parentheses tell us this, it's what the mathematics says. So in calculating 6 times the quantity, 4 plus 8, we have 6 times the quantity, 4 plus 8, equals 6 times 12, and 6 times 12 is 84. Now the question becomes, could we have used the distributive property here? Could we have actually done the multiplication first? And the answer would be yes, we could have. But we would have to multiply the 6 times the 4 and get 24, and the 6 times the 8 and get 48, and then add those two answers together and get 84. So it's not that using parentheses discounts the distributive property. It's just that it's another way of looking at it. I can use the distributive property here, or I can use the parentheses in terms of postponing the order of operations. So with the order of operations, the first step is check for doing parentheses, if it's possible. If you want to do them, fine. Don't want to do them, that's a decision you have to make. And then do exponents, multiply, and then add. And please remember, no PEMDAS. What we have found in our work with students and teachers is that basically PEMDAS becomes this quick draw type of thing that they will just say, I know the answer, it's PEMDAS. And when it comes to applying PEMDAS, it's really inaccurate because PEMDAS really says, the letters of PEMDAS say, parentheses, exponents, multiplication, division, addition, subtraction. And really, in a sense, multiplication and division can be seen as a similar operation, and so can addition and subtraction, especially when you get into the integers with addition and subtraction, and when you get into the rational numbers with multiplication and addition. And plus the fact, as we hope we have shown you today, there is no reason for PEMDAS. If we start with the addition and multiplication in the early grades, in 3rd and 4th grade, when children are solving those problems, and then move on to using the exponents with the order of operations, when the children get into 5th or 6th or 7th grade, when exponents are studied, there should be no problem with the PEMDAS. There should not be a use of the PEMDAS.
I just wanted to give you a little bit of history, and Frank has kind of alluded to a little bit of this. Everybody wonders, where did the order of operations come from? Is it this magical mathematician way of looking at things? It's not magic, and it started around the 16th century of looking at how we do things in a logical order, but as it appears, if you read the way we do things, it's more the language of how this problem is being solved. So it's more the literacy in the language of mathematics and the correct logical way of looking at a problem. So the history behind this is that it's not just a group of mathematicians sat down one day and stated, well, we're going to come up with this rule. That's not where it came from. If you think of multiplication as repeated addition, you have to find that number before you can add it to something else. So it's that logical way of looking at it. It's the language. And if you read the problem, when a student reads the problem and they read it, it's just the logic and the language of how to solve the problem. So
the other thing also involved in this is the idea that when you really get into the algebraic structure, or let's say the upper level number systems like the rational numbers and the integers, the order of operations really doesn't become a problem, because what you can do is you can substitute all of your subtractions for the addition of the negative, or the addition of the opposite, I should say, and all of your divisions as the reciprocal. And once you do that, then all you do is you multiply first and then you add. And it just seems to us that sometimes these problems are put on exams and whatever just to make it difficult as opposed to more complex. And so as a result, you have to be careful as you develop this to make sure that the children truly understand the mathematics behind it, the mathematics structure behind it in the arithmetic, and then as they get into the middle school and the upper grades, the mathematical structure behind the algebra.
Because remember, we've said it before, algebra is a generalization of arithmetic. So this afternoon we were trying to show you that if you start with the arithmetic and build on it, you can end up with making the generalization so that they understand that it's moving through the grades, how it's being developed, not just giving you a rule or giving you a formula that states that the distributive property is multiplication over addition. What we try to do is to show you how it develops, how they can see the structure being built upon. And so what you're looking at is saying that by the time they reach the algebra, they'll say, oh, I remember how to do that. And you're looking at it as moving across the grade. And as Frank has stated, you can start this as early as second and third grade to build upon it. The order of operations is just a logical way of looking at something. It's, again, telling them, and how do we read? We read from left to right. So when you're looking at this problem, you're going to start on the left and move to the right, and you're going to read the problem. So in reading the problem, it's just a logical way in the language of solving the problem. So that's a little bit of the history, and what we hope to do here this afternoon is showing you how it grows into the generalization of the algebraic structure.
And this is also a point when you're looking at textbooks or materials. The question is, when is the order of operations introduced? If the order of operations is introduced, or even distributive property, let's put it that way, if they are introduced in the upper grade, this might not be good for students because it's for them, as you well know, it's brand new. If it's introduced over the time, over the grade levels, they get used to it. And in a sense, like with the distributive property, it might be as simple in the lower grades as saying, if I'm multiplying 3 times 24, I have 3 20s and I have 3 4s. That, in essence, is the distributive property. And so we hope our presentation today has helped you to understand these two properties, which tend to give both teachers and students a challenge, if I may be kind enough to say it that way, a challenge in how to approach them, as opposed to just telling the children, this is what you have to learn.
Does anybody have any questions? Because if you have a question and you can write it in, we'll answer any questions. Well, I thank you for joining us this afternoon. We hope that we gave you something to think about and that you can take this structure and help you to be able to introduce the distributive property and the order of operations by using the various methodologies of looking at it. And as our videos tried to show you, going through looking at the stages of being able to build upon the operations and making sure that the students can go from looking at the manipulative in the end to the symbolic. And that's what it's about, looking at developing it through the concrete and moving it